Hello children, today I am going to continue with the topics of moving charges and magnetism. In the last class we discussed about the construction working principle of moving coil galvanometer. So I am going to continue with moving coil galvanometer. So let us make a very quick recap of what about the theoretical expression we got for the current flowing through a moving coil galvanometer. We started from the deflection torque. What about the deflection torque produced in the rectangular loop or coil? That was tau is equal to beta cos alpha. Beta cos alpha. What about the restoring torque developed due to the suspension twisting? That is tau is equal to k alpha. At equilibrium, obviously k alpha is equal to beta cos alpha. We make a formula for current. I is equal to k by NBA into alpha by cos alpha. K by NBA, we said it is constant. It's called galvanometer constant, that is G into alpha by cos alpha. Now if I am going to establish a proportionality, we will be able to see that is I is proportional to alpha by cos alpha. We arrived up to this equation in the last class. We spoke about the linearity. Since alpha is the deflection produced, I is the current flowing through the galvanometer. You are able to see alpha is in both the numerator as well as denominator. This means I is not directly proportional to alpha. If such a case, we are going to see a linear scale of measurement cannot be done. A linear scale of measurement cannot be done. To have a linear scale, there should be a linear variation of the two quantities. This means we are supposed to achieve I should be proportional to alpha. We are supposed to achieve I should be proportional to alpha. So for that reason, if we are able to focus this diagram, the shape of the magnet is plane. You are able to see what about the shape of the two poles of the magnet. It is plane, and you can see the perpendicular distance is b cos alpha. The perpendicular distance is b cos alpha. So by some mean, if we can remove that cos alpha, we are going to see in the coming part, by some means if we can remove cos alpha from the perpendicular distance, surely we may be getting the deflection torque to be beta, B-I-N-A. In that case, if I am going to equate this, beta is equal to k alpha, obviously I may be getting I is equal to g alpha, and I may be getting I is proportional to alpha. For that, in order to achieve a linear scale, the shape of the poles of the magnets are made concave. You can see the diagram. What about the shape you are able to see? Concave shaped pole pieces of the permanent magnet is used to achieve a linear scale. How we are able to achieve a linear scale? You can see for each position of the coil, the plane of the coil is parallel to the magnetic field lines. You can clearly see in the diagram, the plane of the coil is parallel to the magnetic field lines for each position. This means always the perpendicular distance will be b only, that is breadth. Always the perpendicular distance will be equal to b. So ultimately, how the deflection torque will modify now? It becomes beta. Now once again, what about the restoring torque developed? Tau is equal to k alpha. Now this equation will become k alpha is beta, and it becomes I is equal to k by NBA into alpha. It becomes I is equal to g alpha, and ultimately I am going to get I proportional alpha. So such a galvanometer is said to have a linear scale of measurement. So the type of magnetic field we are getting from a concave shaped pole pieces is termed as a radial magnetic field. What I can say, what is the type of magnetic field we are going to get from concave shaped pole pieces? It is termed as a radial magnetic field. What is the special characteristics of radial magnetic field? For each position of the coil, what about the plane of the coil? The plane of the coil is parallel to the magnetic field lines. So if such a case, always the perpendicular distance between the two forces will be b only instead of b cos alpha. By putting in the basic equation, I arrived at I is proportional to alpha. So once again I am going to make a complete recap of moving coil galvanometer. Basically a moving coil galvanometer is used to detect very small current in electrical circuits. On what principle a moving coil galvanometer is based? It is based on the principle that when a current loop is suspended in a magnetic field, it experiences a torque. Regarding constructional details, it consists of a rectangular coil ABCD. It is suspended between two concave shaped pole pieces of a permanent magnet. It is suspended from a T-shaped hook called torsion head. The type of wire used for suspension is phosphor bronze, and it is kept between two concave shaped pole pieces. The entire setup is enclosed in a non-magnetic case to avoid the disturbance of air. In addition, two screws at the base called leveling screws to align the galvanometer. In addition, two screws at the sides, they are called binding screws to connect the galvanometer to the external circuit. The principle or working behind the moving coil galvanometer already we discussed. So when a current say I enters the coil of the galvanometer, each arm will experience a force. F1 and F2 are the forces on the upper and the lower arm. F3 and F4 on the two sides. F1 and F2, they are equal in magnitude, opposite in direction, with same line of action. As a result, they cancel off each other, while F3 and F4 with different line of action gives rise to a torque. What about the deflection torque produced is Bina cos alpha, that is Bina cos alpha, and the restoring torque in the suspension wire is K alpha. At equilibrium we equated, and what we arrived is I is equal to K by NBA into alpha by cos alpha. K by NBA was given a term called galvanometer constant. So we arrived at I is proportional to alpha by cos alpha. Since I is not directly proportional to the deflection produced, a linear scale of measuring the current cannot be done. The type of pole we used in that case is a plane shaped. And recall the diagram. What type of magnet we used in that case is a plane shaped magnet. To avoid that, in order to have a linear scale of measurement of current, we used concave shaped pole pieces. What about the characteristic property of concave shaped pole pieces? For each orientation or for each position of the coil, the plane of the coil is parallel to the magnetic field lines. So what about the perpendicular distance between the two forces? Initially it was B cos alpha, now it becomes B, that is equal to the breadth of the rectangular loop. So by replacing Bina cos alpha with Bina and equating with the restoring torque, we arrived at I is equal to G alpha, I is proportional to alpha. So such type of galvanometer is said to have a linear scale of measurement. So with this I am going to get into my next topic. We are going to discuss about the sensitivity of a galvanometer. We are going to discuss about the sensitivity of a galvanometer. When a galvanometer is said to be sensitive, if it gives a large deflection when a unit current flows through it, or if it gives a large deflection when a unit potential difference is applied across it. So once again, a galvanometer is said to be sensitive when a unit current flows, it gives a large deflection. Similarly, when a unit potential difference or voltage is applied across it, if it gives a large deflection, that type of galvanometer is said to be more sensitive. Or simply, it shows a large deflection even for a small current, if it shows a large deflection for a small voltage applied across it. That type of galvanometer is said to be a sensitive galvanometer. Regarding sensitivity, there are two types of sensitivity we are going to discuss. One is current sensitivity, the second one is voltage sensitivity. So let us get into current sensitivity. So what is current sensitivity? I am going to use one of the equation that we used in the last case. You know the current flowing I is equal to K by NBA into alpha. We arrived, this is one of the intermediate equation that we did in the last derivation. You just make a shifting, you make alpha by I, make a ratio of alpha by I, it becomes NBA by K, alpha by I, and it becomes NBA by K. Here alpha by I is called current sensitivity. Alpha by I is called current sensitivity. So what is current sensitivity? It is the deflection produced in the coil when a unit current flows through the coil of the galvanometer. What about the definition we can give for current sensitivity? It is the deflection produced is alpha when a unit current flows through the coil of the galvanometer. So mathematically current sensitivity is denoted by alpha by I. Current sensitivity is denoted by alpha by I, and by this we are getting NBA by K. So once again, what is sensitivity of a galvanometer? A galvanometer is said to be sensitive if it gives a large deflection even when a small current flows through it, or if it gives a large deflection even when a small voltage is applied across it. That type of galvanometer is said to be a sensitive galvanometer. Sensitivity is of two category. One, it is current sensitivity, another is voltage sensitivity. So what about current sensitivity? It is the deflection produced when a unit current flows through the coil of the galvanometer. Mathematically it is alpha by I. Alpha is the deflection produced, I is the current flowing. Alpha by I is termed as current sensitivity. So mathematically alpha by I, we are going to get it is NBA by K. Get into the second type, voltage sensitivity. So you know, just by making a small alteration in the denominator, what I am going to do, already we know current sensitivity is alpha by I is equal to, it is NBA by K. Already we derived this. Just I am going to multiply R in the denominator. Obviously for neutralizing this I am going to make R on both sides. So we are able to see what is IR is V, that is voltage, and this is termed as voltage sensitivity. So once again, what is voltage sensitivity? It is the deflection produced when a unit voltage is applied across the ends of the coil. So once again, what is voltage sensitivity? It is a deflection produced when a unit voltage is applied across the coil. Mathematically it is alpha by V. How we arrive? By multiplying R in the denominator of current sensitivity, that is alpha by IR. So ultimately we are going to get a formula for current sensitivity as NBA by K, and for voltage sensitivity we got a formula, it is NBA by KR. Now let us speak some of the factors affecting current sensitivity. Let us speak some of the factors affecting current sensitivity. So you just focus the formula. Current sensitivity depends on the number of turns, the area of cross section, the strength of magnetic field, and the restoring torque per unit twist produced in the suspension wire. Now you are able to clearly see current sensitivity is directly depending on these three factors. This means by increasing the value of N, by increasing the value of A, and by increasing the value of magnetic field, the current sensitivity can be increased. The current sensitivity can be increased. Similarly, how current sensitivity is depending on the restoring torque per unit twist, that is K, it is inversely proportional. So by decreasing the value of K, or by selecting the suspension wire with low value of K, the sensitivity can be increased. For that reason, to have a low value of K, the type of material we used in the moving coil galvanometer is phosphor bronze wire. You are able to recall the diagram. The type of wire that is used for suspension of the coil is a phosphor bronze wire. The value of K for phosphor bronze is small. Obviously the sensitivity will be large. If I want more sensitivity, by beating the wire into sheet, the sensitivity will further increase, that will further decrease the value of K. And if I want to have much more sensitive galvanometer, we are going to use quartz fiber as the suspension wire. Next, but here a little critical thing you are able to see, the current sensitivity can be increased by increasing the value of N and A up to a certain limit only. There is a restriction on increasing the number of turns and the cross sectional area. You know, ultimately by increasing the number of turns, the resistance will increase, and if I am going to increase the area, the size of the galvanometer will be increasing, or it becomes large. So there is a limit, or there is a restriction in increasing N and A to increase the sensitivity. So what are the two left out options for having a greater sensitization of the galvanometer? By increasing the strength of magnetic field, so much stronger permanent pole pieces are used. In addition, by selecting low value of K of the suspension wire. For that we are going to use phosphor bronze wire, yeah, quartz fiber. Now one more very important fact you should know. Now a question if I am going to ask, increasing the current sensitivity, whether it necessarily increases the voltage sensitivity. So it's a most important content what I can say in this sensitivity topic. What is the question? If I am going to increase the current sensitivity, whether it is necessarily increasing the voltage sensitivity. Let us explore into this. The answer is no. Increasing the current sensitivity not necessarily increases the voltage sensitivity. How? You are able to see. If alpha by I, if I am going to say n, I am going to take one of the factor as n. Say by increasing the number of turns, the alpha by I value increases. But you know, when the number of turns increases, obviously the length will increase. When the length increases, the resistance will increase. If the resistance increases, surely you are able to see what happens. Alpha by V will decrease because resistance is inversely related. So you are able to see if the resistance increases, the voltage sensitivity will decrease. So this is the common fact that by increasing the current sensitivity, it is not necessary that the voltage sensitivity will increase. So it is one of the common question that will creep in the question paper for 1 or 2 marks. So once again I am going to consolidate what about the factors affecting sensitivity. What was the first thing we said? By increasing the value of number of turns, area of cross section and magnetic field, the sensitivity can be increased. By decreasing the value of K, that is the restoring torque per unit twist of the suspension wire, and for that reason only we are going to use phosphor bronze wire. Yeah, I am going to use quartz fiber to have a low value of K. In addition, the value of N and A cannot be increased beyond a certain limit because it will increase the resistance and size of the galvanometer, and at last increasing the current sensitivity not necessarily increases the voltage sensitivity. Let us speak about the accuracy of a galvanometer. So what do you mean by accuracy of a galvanometer? Basically it implies the extent to which the current can be measured accurately. Basically it is the implication to the extent the current can be measured accurately is termed as accuracy, but it is just a literal meaning. So what about the definition for accuracy of a galvanometer? So accuracy of a galvanometer is defined as the reciprocal of relative error. I am going to define accuracy of galvanometer as the reciprocal of relative error in measuring the current. So what about the definition for accuracy of galvanometer? It may be defined as the reciprocal of the relative error in measuring the current with the galvanometer. You know what is relative error for measuring the current? I can say the relative error in measuring the current can be written as di by I. And accuracy, what I give a word for accuracy is the reciprocal. Reciprocal means 1 by di by I is termed as accuracy of the galvanometer. Now let us establish on what factor the accuracy will depend. For that I am going to say, if alpha is the deflection produced and I is the current, you know I is directly proportional to alpha. Similarly, let us suppose that if d alpha is the error in the deflection, di will be the error in the current. So I can write di is proportional to d alpha. So mathematically what I can write is di by I is equal to d alpha by alpha. So you use this in this equation. So what about accuracy I am going to get? Accuracy will be alpha by d alpha. Alpha by d alpha. This means accuracy is directly depending on the deflection produced. This means if I am going to get a large deflection, the galvanometer will be highly accurate. What I can conclude, if the galvanometer gives a large deflection, obviously the galvanometer will said to be highly accurate. So once again I am going to say what accuracy of a galvanometer implies. It implies the extent to which it can measure the current accurately. Number 2, it is the reciprocal of relative error in measuring the current with the galvanometer. That is, it is 1 by di by I. You know relative error is di by I in measuring the current. Reciprocal will be 1 by di by I. That becomes a definition for accuracy of galvanometer. And by this mathematical reduction, you know if I is proportional to alpha, d alpha and di are the respective errors. Mathematically di by I is equal to d alpha by alpha. I am using this in the accuracy formula. So what I am going to get is accuracy is equal to alpha by d alpha. This means it directly depends on the deflection. If larger is the deflection, obviously the accuracy of the galvanometer will be accurate, high I can say. So with this I am going to get into my next topic. What the next topic says, we are going to convert a galvanometer into an ammeter. We are going to convert a galvanometer into an ammeter. Already you know what is an ammeter. Ammeter is basically a current measuring device. Ammeter is basically a current measuring device. Here we are going to convert a galvanometer into ammeter. So let us suppose that I want to convert a galvanometer into an ammeter of desired range. Say it is 0 to I ampere. What about the range is 0 to I ampere? This is the desired range of ammeter that I want to obtain. Let Ig be the current for which the galvanometer gives full scale deflection. What I am assuming, let Ig be the current that flows through the galvanometer, and due to that flow I am assuming the galvanometer will give full scale deflection, means it gives maximum deflection. So these are the considerations. So I want to convert a galvanometer into an ammeter of desired range. What about the ranges? 0 to I ampere. Number 2, what about a current Ig flows through the galvanometer and it gives full scale deflection, and the value of Ig is much smaller than I. To be very clear, I is the range, Ig is the current that flows through the galvanometer. The value of Ig will be very small when compared to the value of I. So in order to convert a galvanometer into an ammeter, I am going to consider, say this is a galvanometer. I am going to connect a resistance S. I am going to connect a resistance S parallel to the coil of the galvanometer. I am going to consider a resistance S connected in parallel to the coil of the galvanometer, such that when a current I enters, a current Ig flows through the galvanometer and the remaining I minus Ig flows through the resistance S. So once again, in order to convert a galvanometer into an ammeter of desired range, I connected a small resistance S in parallel to the coil of the galvanometer. It is also called shunt resistance. So the value of S is so adjusted that when a current I enters, only a current Ig flows through the galvanometer. The remaining, obviously you are able to see the branching occurs, I minus Ig flows through the shunt. Now I want the value of S mathematically, I want the value of S. The S will decide the conversion values. You are able to see the potential difference for S and G are same. Obviously they are connected across the 2 points. So what about the potential difference across G will be the potential difference across the shunt. So what about the potential difference, Ohm's law, that is V is equal to IR. What about the potential difference across this is Ig is the current and say G is the resistance. What I can say, IgG is the potential difference across the 2 points. Similarly, you speak for S, S will be the current will be I minus Ig. The current is I minus Ig and the resistance we assumed as S. So once again, the potential difference across the galvanometer is equal to the potential difference across the shunt resistance. Obviously, potential difference across the galvanometer is Ig into G. Potential difference across the shunt is I minus Ig into S. So what will be the formula for S will be Ig by I minus Ig into G. This becomes a formula for shunt. So once again, in order to convert a galvanometer into an ammeter of desired range, a small resistance S is connected in parallel to the coil of the galvanometer. The value of S is so adjusted that when a current I enters, only Ig flows through the galvanometer, the remaining I minus Ig is bypassed through the shunt, such that the potential difference across the galvanometer and the shunt is equal. On equating the two, I am arriving at S is equal to Ig by I minus Ig into G. So let us explore in some of the important facts of conversion of galvanometer into ammeter. So what is the first thing I can say? So what is an ammeter? Basically it is a parallel combination of a galvanometer and a shunt. A parallel combination of a galvanometer and a shunt constitutes an ammeter. The first thing, a parallel combination of a galvanometer and a shunt constitutes an ammeter. Next, let us derive an expression for the resistance of the ammeter. You know, G and S are parallelly connected. Say if Ra is the resistance of the ammeter, what I can write is 1 by Ra. Ra stands for resistance of the ammeter, since they are parallelly connected. So 1 by R will be 1 by R1 plus 1 by R2. So here I am assuming 1 by Ra is the resistance of the ammeter, the entire combination. It will be 1 by G plus 1 by S. So obviously you are able to see G plus S by GS. Yeah, reciprocal Ra is equal to GS by G plus S. Now already we said shunt, the value of shunt is very small when compared to the resistance of the galvanometer. So I can neglect this S from the denominator. So once again, the value of S is very small when compared to the resistance of the galvanometer. So from the denominator I can remove this S. So you are able to see GG cancels. So what about the resistance of the ammeter is approximately equal to the shunt resistance. Resistance of the ammeter is approximately equal to the shunt resistance. This means if I am going to speak about the resistance of the ammeter, it is basically a low resistance instrument. Since the value of shunt is already small, so what about the conclusion I can draw based on this expression? The resistance of the ammeter is very low. Or I can speak, if a question is asked, what about the resistance of an ideal ammeter? If a question is asked, what about the resistance of an ideal ammeter? You should say it is 0. It possesses 0 resistance. An ideal ammeter possesses 0 resistance. Now let us speak how an ammeter is connected in a circuit. Obviously ammeter is used to measure the current in a circuit, and if you are supposed to connect an ammeter in a circuit, it will always be connected in series. It will always be connected in series, and you know the reason, because as it possesses low resistance, the resistance of the circuit remains unchanged. Since it is a low resistance instrument, obviously the resistance of the circuit practically remains unchanged, and ultimately the current of the circuit is also unaffected. So what is the basic behind why it is connected in series? Already I said it is a low resistance instrument. It does not alter the resistance of the circuit. As such, what is the consequence of that? It does not change the current flowing in the circuit, or the current flowing remains unchanged. So that becomes the basic concepts related to conversion of galvanometer into ammeter. Let us get into the conversion of galvanometer into voltmeter. How a galvanometer can be converted into voltmeter? Say this is the coil of the galvanometer. I am going to connect a resistance R in series with the coil of the galvanometer. In series with the coil of the galvanometer, this construction becomes a voltmeter now. So once again, there we connected a small resistance in parallel to the coil. Here I am going to connect a resistance R in series with the galvanometer coil. The value of R is so adjusted that when a potential difference V is applied across the combination, what about the value of R? R will decide. So what about the value of R? The value of R is so adjusted that when a potential difference V is applied, a current Ig flows through the combination. A current Ig flows through the combination. Since the potential difference is V, what about the current flowing is Ig through the combination. So what about the controlling value here is R. So how we can have a mathematical expression? What about the current flowing? Ig is equal to, I is V by R. It becomes V by G plus R. And make a shuffling. G plus R will be V by Ig. So what about the value for R? It will be V by Ig minus G. So this becomes a formula for resistance that is required to convert a galvanometer into voltmeter. Once again, in order to convert a galvanometer into voltmeter, a resistance is connected in series with the coil of the galvanometer. So what about the resistance? You are able to see resistance, how the value of R is adjusted. When a V is applied across the combination, a current Ig enters the circuit. Mathematically we are arriving at R is equal to V by Ig minus G. Now let us speak about the resistance of voltmeter. What about the resistance of voltmeter? Say RV is the resistance of voltmeter. Say it's a series combination. So directly G and R are connected in series. So we are able to see G has a finite value, R has also a finite value. So obviously it is a high resistance instrument. It is a high resistance instrument, and for that reason it is always connected in parallel with the circuit, because if it is connected in parallel, due to high resistance, the potential difference across the conductor will not change. So once again I am going to make a nutshell. A series combination of galvanometer and a resistance constitutes a voltmeter. The resistance of the voltmeter so formed is very large when compared to the galvanometer from which it is made. A voltmeter is a high resistance instrument. What about an ideal voltmeter? It possesses infinite resistance. If I am going to speak how it is connected, it is always connected in parallel. This is because as the voltmeter will not practically draw any current due to high resistance, the potential difference across the conductor will not decrease. With this, I am going to end my session. Take care of yourself.